my name is Chris Harris and I'm from Allery Chemistry, and this video we're going to look at reaction types and organic chemistry. This video is an A-level bridging video, so it's basically designed to pick up on the knowledge that you've learned from GCSE and try and link it to some concepts that you'll see in A-level chemistry. So it's designed to go through some of the areas that you've looked at GCSE, so it shouldn't be too dissimilar to what you've seen before, but introduce some of the new concepts. So that's the crux of it, really, and it's really there to give you a little bit of a head start if you are going to do A-level chemistry next year. But if you are, there is a YouTube channel, so my YouTube channel, which is called Allery Chemistry. There is a full range of A-level videos on there that cover all the main exam boards, such as AQA, Edexcel, OCR, and OCR Salters. So go and have a look on there. They're all for free. But for this video in particular, I've done a quiz as well. It's an electronic quiz, a multiple choice quiz with 10 questions on there. It's basically designed to see if you can understand some of the content that's been put across in this video. It all marks itself as well, so if you put in the answers there, it will give you feedback instantly, so you know if you got the answers right or if you haven't, and obviously you've got the video to refer back to if you're not too sure on some of the answers there. So let's make a start. So let's look at organic chemistry. And you might have seen, in fact you will have seen some organic chemistry at GCSE. So this is going to go through some of them elements there. But you've seen that organic chemistry is mainly based in carbon and hydrogens, mainly hydrocarbon-based substances, and they're also known as organic compounds. You can see some in the picture there, such as naphthalene, glucose, ethanoic acid. So these are all organic compounds. They don't look very exciting. They're normally colourless liquids and white powders, but they form a large basis of medicines in the UK, paints, for example, so paints and dyes and colours, etc. So they play a huge role, and actually most of our body is organic chemistry. So it's very important. So they split into families because it's such a huge area, and we categorise them into different families, and we call it. They give it a very interesting name called Homologous Series, and you'll see more of them later. But each homologous series has a similar pattern, and they have a pattern in terms of reactivity. So they react in a similar way, and their properties are quite similar as well. So you'll see that later on. And you would have seen some classic organic compounds of things like alkanes and alcohols, and you'll see a lot of that. But the key thing is naming them and drawing them and being able to identify organic compounds and substances. And it is quite a broad area of chemistry. So we're going to go through the different ways in which they can be displayed and the ways in which they're named as well. We're going to go through a little bit of an introductory. It does get a little bit more complicated in A-level, which we won't go through in this video, but it will give you an idea of the types of things that are talked about at A-level. Okay, so let's look at a homologous series first. So a homologous series is a group of compounds that have the same functional group and general formula. So we use something called a general formula to work out the molecular formula of a compound. So a general formula is a bit like algebra in maths. So we can have a fixed formula and we can apply that and put different numbers in to get an answer. So we do the same in chemistry. So alkenes have a general formula of CnH2n, for example. So where n is the number of carbon atoms. So for example, if we've got an alkene with 23 carbons in, then that's going to be C23H, and it's going to be 2 times 23 because it's 2n, so it's going to be C23H46. So it's as simple as that. So they can be useful because you get some big compounds in organic chemistry. So successive members of the same homologous series, so that same family of chemicals, increases by CH2 every time. So for example, the general formula of an alcohol is CnH2n plus 1 OH. So that's the general formula there. So methanol is CH3OH. Ethanol is CH3CH2OH, so we've added a CH2. Propanol is an extra CH2, and butanol is another CH2. So you can see there's similarities here. All we're doing is extending the carbon chain. Okay, so we need to come across some of these homologous series and how we can name them and some examples of these, because you'll come across these and you may have seen some of these already as well. So alkanes end in ane, and an example is butane. So alkanes are just a straight hydrocarbon chain. You might have seen them as well. Alkanes, which are branched, So these have alkyl, for example. You might not have seen these too much at GCSE. You'll see them a lot more at A level. But this is just an introduction to it. So for example, methyl propane, which is that compound there. Alkenes have ene at the end of it. So propene, for example. So very similar to propane. You've got to be very careful, but they have, obviously it has ene on the end of it instead. Alcohols have ol at the end. They end in ol. So for example, ethanol. So you can see they all have a very similar structure. It's eth, prop, bute. It's the ending which changes. So alcohol is ol. Aldehydes, you won't have seen aldehydes, I doubt, at GCSE. If you have, then it wouldn't have been that much. But aldehydes end in al. So they, for example, propanal, that's an aldehyde. All ketones end in -one. So that's propanone, which is CH3COCH3. So again, you might not have seen that at GCSE. You'll come across that a lot more at A level. Carboxylic acids, so you might have seen that at GCSE. We're going to see it a lot more in A level. Ends in oic acid, so for example, butanoic acid. Halogenoalkanes, you might not have seen these at GCSE. You're going to see it a lot more at A level, certainly, but it's basically just an alkane with halogen attached to it. So you can get fluoro, chloro, bromo, iodo. So for example, bromoethane. Cycloalkanes, you won't have seen these at GCSE. They're basically just alkanes that are looped up into a circle. You'll see some examples later on in this video just so you can see them. But for example, a 5-carbon ring is called cyclopentane. So cyclo and then ane at the end of it. And esters, you might have seen esters at GCSE, but they have two different parts. You've got alkyl, whatever the hydrocarbon is before, and then you end it in anoate at the end. So for example, methyl ethanoate has a methyl group, so that's like methane, and then ends in ethanoate. So you might have seen that at GCSE as well. So these, you're going to see these quite a lot at A level, and it's mainly just a case of practicing it. So by the time, when you see, you'll see this all the time, and you'll be writing these out, drawing them out, using the names all the time, and they'll just become second nature. It does seem quite a long list, but it does become second nature when you have a lot of practice in it. Okay, so let's look at types of formula. Now, there's loads of ways in which you can write down, describe organic compounds. And so we're going to look at the different types of formula and the different ways in which they can be represented. And you'll see all of these at A level, and you might have seen some at GCSE. So we've looked at general formula already. It's an algebraic formula that can be applied to chemicals in the same family. So for example, alkanes, alkenes, alcohols, etc. So we see loads of different types. So alkanes have the formula CnH2n plus 2. Alkenes is CnH2n, and alcohols is CnH2n plus 1 OH. So these are the algebraic formulas that we can use, and we've seen an example of how that can be worked before. So the next type is a molecular formula, and actually this is probably one you've seen more often at GCSE, is the actual number of atoms in a molecule or an element. So for example, ethane is C2H6. Okay, structural formula, this is the arrangement of atoms in a molecule without actually showing the bonds. So it gives you a little bit more information in terms of how it's structured. So, for example, butane 1-ol, don't worry about the one bit, you'll come across that a little bit more into A level. But you can see here, what we've done is we've actually broken it up into chunks, but there's no bonds being displayed. So it's CH3, CH2, 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 OH, and it allows us to see how that molecule is actually built up. The next type is skeletal formula. You may not have seen this at GCSE, and it looks the most bizarre formula I think you'll ever see. But it is massively useful to organic chemists because some of these molecules are so big and repetitive. It's just CH, CH, CH. We can take the CH bits out because we know that it contains them and just literally draw lines, and it speeds it up much, much quicker. So chemists like shortcuts, basically. They like to keep things simple. So we show the bonds of a carbon skeleton only, and hydrogen and carbon atoms are not shown in the skeletal formula, but functional groups are. So for example, we'd seen butanol before. Butanol, instead of writing CH3, CH2, 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 OH, we literally draw a zigzag line. And the rule is every point on the zigzag line is a CH. Now we know this is an end carbon, so this is going to be CH3. That's CH2. that's CH2, that's CH2, and then OH at the end. So we've got 1, 2, 3, 4 points, and this one is obviously bonded to the OH, so that is butanol. And you can see, obviously drawing that is a lot quicker than it is actually writing CH3, CH2, etc. So you will see skeletal formula quite a lot in organic chemistry, so get used to it. Right, okay, so the displayed formula. Let me just get rid of that. There we are. Okay, sorry about that. Okay, so types of formula is a displayed formula. So it shows the arrangement of atoms, showing all the bonds in an atom and the molecules. So this is a lot more detailed and is quite useful when we're drawing mechanisms, and you'll see reaction mechanisms later on. So for example, 2-chloropropane is 3 carbons, and then you've got all your hydrogens and chlorines. In this case, you've got a chlorine in the middle carbon. Again, don't worry about the 2 bit on there. But it's just showing you all the bonds, so you can see how the carbon and what's actually bonded to that. So you will see that quite a bit, again, in A-level chemistry, and you would have seen that at GCSE as well. Okay, so let's have a look at alkanes. It's the first type of organic compound. So alkanes are saturated hydrocarbons. That means they've got no double bonds in them, so they're fairly straightforward, and they have that general formula of CnH2n plus 2. So alkanes are hydrocarbons, and that means they contain hydrogen and carbon only. And they're saturated, which means each carbon is bonded 4 times with the maximum number of hydrogens possible. Okay, so some examples there. We've got methane, ethane, propane. So they're the first 3 there. And that's showing you a saturated compound. Cycloalkanes are slightly different. They have the general formula of CnH2n. We've seen some cycloalkane just before. You won't have seen these at GCSE, so these will be a little bit new. But like I say, it's just linking along like a 5 carbon, in this case 5 carbon hydrocarbon, and linking it up into a ring. So we call it cycloalkanes. They're still saturated. They don't have any double bonds in them, but they do have obviously 2 hydrogens missing to allow them to bond together. Remember, carbon needs to bond 4 times. Okay, so the shape of alkane molecules. Now, this will definitely be new. So this is a little bit of A level here. Alkanes are actually not flat. They have 3D structures, and they form something called a tetrahedral shape around a carbon atom. And basically, this is looking at methane. So this is 1 carbon with 4 hydrogens. It has a bond angle of 109.5. Now, you will need to know that at A level, but don't worry too much about it at the moment. What we're looking at is a 3D structure, and this gives us what we call a tetrahedral shape. Because they have a single bonds, they're just single covalent bonds, so each one of these lines is a single covalent bond shown in a 3D space. They can rotate, so they can actually move and twist and shape, and that's quite important when we're looking at a hydrocarbon, for example. So you see the cyclo bit, we can twist hydrocarbon chains into shapes that we require, which is very useful when we're designing medicines, because they need to fit on a substrate and an enzyme, for example, to cure a disease or to block certain chemicals from getting into the bloodstream caused by viruses and bacteria, etc. So designing the shape of a chemical is really important, and thankfully hydrocarbons can be twisted into numerous different shapes because the bond allows a rotation around that. So that's really, really useful. Okay, so looking at properties of alkanes. So alkanes, as we know, we can join them together and form long hydrocarbon chains. Now, the longer that chain is, the more forces that we have between it. And you would have seen intermolecular forces in video 2. So if you're not sure about that, then go and have a look at video 2, because it's quite an important concept, and it reoccurs quite commonly in A-level chemistry. So basically, longer straight chain hydrocarbon chains have loads more intermolecular forces between the chain, and this means that more energy is required to break the forces between that, and that means longer hydrocarbon chains have higher boiling points and higher melting points. And so this can be clearly seen in everyday life. So, for example, if we look at a hydrocarbon, longer hydrocarbons are more viscous and are thicker, because they need more energy to actually break them or turn them into a liquid or a gas. So bitumen, for example, is used in tarmac, and we know that tarmac has got carbon chains over 50, so they're really long chains. and we know that tarmac is quite thick. It's a solid, and it's a lot thicker than, say, petrol or unleaded, which has only 5 to 9 carbons and is very liquid, completely. Much different to tarmac. So you can see the physical properties. Both are made from hydrocarbons, but their physical properties are different, and that's because of the length of the carbon chain and the intermolecular forces that holds them together. So that's quite important. Okay, so volatility as well as another aspect linked with the same principle. Volatility is how easily something evaporates, how easily it turns into a liquid or a gas. And this decreases as the chain length increases. Again, petrol is more likely to evaporate than tarmac on a hot day, thankfully. Otherwise, you'll get roads just evaporating, on a hot summer's day. But petrol will do that, so it is a lot more volatile. Okay, alkanes have strong covalent bonds between the atoms, and that gives them very specific scientific properties. So they have lots of strong covalent bonds, as you can see here. This diagram shows all the different bonds there. It means require a lot of energy to break them. This makes alkanes fairly unreactive. They burn easily, of course they do, because they're good at, some of the hydrocarbons burn easily because they're good fuels. But in terms of a reaction, in terms of reacting with other substances, it's really difficult for them to do that. And so for this reason, it's really difficult for them to make polymer chains. And alkenes, you'll see later on, they are, but they don't really react to do a lot, really. They are useful as fuels, as I say, so they can be used for that use, and they actually burn with a clean flame, and you would have seen that at GCSE. Okay, so let's look at an example of that. So let's look at the complete combustion of alkanes. So alkanes burn in oxygen, and there's got to be a plentiful supply as well for it to burn completely, and it forms carbon dioxide and water. Now, alkanes are good as fuels, as we say, because most of them burn readily, and they're useful in, for example, powering a car. And they're used they're also used to make electricity. So we can, for example, burn gas or burn coal to make electricity. A lot of electricity in the UK, particularly, is going into wind generation and renewable sources, but there are still some which rely on fossil fuels to produce electricity, and also obviously to use to heat houses. So you might have gas boilers, for example, or you may have oil heating. So the complete combustion of butane is a classic example. So butane plus oxygen produces carbon dioxide and water. So you may have seen this at GCSE as well, which is the combustion of a fuel. Okay, so let's look at alkenes, which is another group in organic chemistry. These are unsaturated, so all that means is they have a double bond in them, and they have the general formula CnH2n. So alkenes are hydrocarbons, so they contain carbon and hydrogen only, very much the same as alkanes as well. They're unsaturated, so like I say, there's one double bond in there, and they undergo something called addition reactions. So you'll see that later, but basically these are substances which add on to a double bond. So ethene is CH2CH2, and butene is CH3CH2CH2. So you can see here that both of them have an alkene, but because we've got a double bond, then we can't have four or three hydrogens, around this one here. We can only have two, because this carbon has got 1, 2, 3, 4 bonds already, and so is this one. So that's the main difference. Double bonds have loads of electrons in them, so this is going to be quite useful because it makes them quite reactive, and you'll see that later. Cycloalkenes, just like cycloalkanes, is pretty much the same, except we're looping a long chain into a ring. So this is cyclopentene, for example. Now, isomers, you may have come across isomers in GCSE, but isomers exist in alkenes, and you get two types. So one is to do with the position of the double bond. So one's to do with the position of the double bond, and one is to do with the rotation of the double bond, which is quite restrictive. I'll come on to that in a moment. Isomers is basically a molecule with the same molecular formula, but it has a different structural formula. And remember, we've gone through them different types of formulas before. So, for example, here we've got butene, which is CH3CH2CH2, which is here. But here we've also got butene as well. Now you'll see in at A level, you actually distinguish these by putting a number in there. So this is butyl-1 and butyl-2. Don't worry too much about that because you'll learn a lot more of that in A level. But basically, these are isomers of each other. So they're both similar, same structural formula. Same molecular formula is the same, but the structure of it is different. So the double bond's in the middle there. Now, unlike alkanes, atoms can't rotate around that double bond. So this is a rigid structure. And so what that means is we get very fixed structures to do with alkenes. So for example, here we've got two isomers here around a double bond. So we've got one that's fixed in this position here, where we've got this group down towards the bottom left. But also we might have some where the group is actually twisted to the top here. So in a long chain, that gives alkenes a very fixed shape. They're quite restrictive. That double bond, these carbons here don't twist around that double bond very easily. So that gives us a fixed shape with alkenes. Okay, so let's look at a test for alkenes. So how do we know if we've produced an alkene? So an alkene is tested, and you might have seen this at GCSE as well, where we use bromine water. And if we add that to a substance that contains an alkene, we get a positive test. So basically what we do is we add the bromine water to an alkene, and if the alkene is present, then we get a positive test. So we shake it, there it is, and then if an alkene is present, we get a colourless solution that's formed. So it's a pretty straightforward test. It goes from brown to colourless. And the reason why is the bromine water is actually reacting with that double bond. Remember we talked about the high electron density in that double bond. It reacts with that and it forms a substance called dibromoalkane. Don't worry about that too much. You'll see that a lot more in A level, of course, but that's the reason why. It's actually that bromine reacting with that. Okay, so alkene properties. So alkanes have, I should say alkenes. They have double bonds between them, so very strong double bonds between the atoms, which give them specific properties. So that should say alkenes, not alkanes. So I'll get that changed. So alkenes, this should be alkenes as well, so I'll get that changed. Alkenes have double bonds with a high electron density, so they are susceptible to a range of chemical reactions. So I've got this one right here. So alkenes are commonly used to form polymer chains, unlike the alkanes, which can't. So they form substances like polyethylene, which is used to make carrier bags. They do burn, but they don't burn with a clean flame like alkanes do. So they're not great for fuels, but they burn with a yellow flame, and they produce a lot of soot as well. Okay, so the bigger the molecule or the atom, just like with alkanes, the more forces we've got because we've got larger electron clouds. So alkenes have very similar boiling point properties to alkanes, but basically the longer straight chain alkenes have more intermolecular forces, so more energy is needed to overcome these forces. This means that the boiling point increases as we go down, as we extend the carbon chain. The same reason again for alkenes, but the longer the alkene chain, the more viscous or thicker that hydrocarbon is. And volatility as well, which is how easily something evaporates, that decreases down the chain as well, for the same reasons it is for alkanes. Okay, so let's look at polymers, because polymers are formed from alkenes, as we've seen. So alkenes are monomers which join to form polymers. Now, you will have seen this at GCSE, more than likely, that you have monomer and polymers. So monomers make up the polymer units, make up the polymers. So polymers can be made from monomer units. You can get different types. You can get natural and synthetic ones. So natural are things like proteins, which you see in your body, and natural rubber. And synthetic are the ones which you make from alkenes, such as crude oil. So polymers have actually been used for a while, and this is a little bit of history regarding, a little bit of background regarding polymers. But in 1844, Charles Goodyear discovered vulcanized rubber. Basically, it's a synthetic rubber. And he added chemicals to natural rubber to make it harder wearing. And actually, we see Goodyear tyres, they still exist. Obviously, Charles Goodyear doesn't, he's long gone. But Goodyear tyres still exist, the company that he formed. And he was actually the first person to discover vulcanized rubber, a synthetic rubber from a natural product. So over the last 100 years, polymers have been developed quite dramatically. There's been a lot of advances in science on this, and we formed substances such as polyethylene, nylon, Teflon, for example, and these polymers have absolutely revolutionized the way we live and work. So it's thanks to plastics that we have some of the products that we have today. But naturally, there are issues, environmental issues to do with plastics, and science is now, taking steps to try and develop plastics which are more environmentally friendly, and still have the same functionality as we have today. We also have, like I say, new polymers, and you've seen such as smartwatches, smartphones, mobile phones, computer screens, tablets, which is what I'm using, which is what I'm using here right now. They all have obviously polymers which allow us to have gadgets which are lighter and smaller. So a polymer, what do we need to make a polymer? So we need the monomer, and we need to join them together with other monomers to make a long polymer chain. So here we're going to make polypropene. And now to make polypropene, we need propene, and we need a lot of these to join up to make polypropene. So here's a propene molecule. It has the double bond in there, and that's going to form our polymer repeat unit, which is this bit here. So there it is there. So what we've done is we've opened up that double bond there, and we are basically having these are called trailing bonds, as you'll see on here. There you go. So this is a repeat unit. So the double bond isn't actually in there, and we have these trailing bonds which extend either side to join with other repeat units, and this makes the polymer chain. Now this one here is showing a repeat unit of 2, so it's made up of 2 monomers, but this can extend quite far. So polyalkenes are saturated molecules. They don't have any double bonds in there, so they're classed as saturated. They're normally non-polar, so they're not very reactive. That could be a good thing because they're durable and last a long time, but not so good if you want them to degrade, when and at the end of life. So there are issues regarding that, but like I say, scientists are developing ways in which we can develop more environmentally friendly polymers. Okay, so let's look at another family, another homologous series, and this one's alcohols. So alcohols contain an OH group, also known as hydroxyl, and that's in its homologous series. So methanol is the first type of alcohol, so this is CH3OH, which is methanol, normally used in antifreeze. Very, very toxic to humans. If you drink, or if you have large amounts of, not even large amounts, you don't even need a lot of it, methanol in the bloodstream, you can actually lose your sight. It is incredibly toxic. So methanol is not so good for humans for consumption. Propanol is another type of alcohol which has got 3 carbons in there. The one in between that is ethanol. Ethanol is normally found in hand sanitizers, for example. It's used in the drinks industry as well. But propanol is the next one up from that. And like with alkenes, we can get isomers as well. So this is also propanol, but the OH group is in the middle carbon, so it's an isomer, as you can see on there. So the positioning of that functional group changes that. Okay, so primary alcohols. You get different types of alcohols. We can get what we call primary, secondary, and tertiary alcohols. So primary alcohol is where we've got an alkyl group. This could be anything, CH3, CH2. It could be anything. We just represent it as R. But basically, a primary alcohol is where the OH group is bonded to a carbon, which is bonded to one other carbon, and that's classed as a primary alcohol. A secondary alcohol is where we've got an OH group bonded to a carbon, which is bonded to 2 other carbons. So that's why we call it a secondary. And a tertiary is where we've got the OH group bonded to a carbon, which is bonded to 3 other carbon groups. So that's what we class as a tertiary alcohol. You'll see that quite a lot in A-level, so you need to be familiar with that, particularly in A-level. You might not have seen it at GCSE, but alcohols can be fit into 3 categories. Okay, solubility of alcohols. So the alcohols are quite soluble, or fairly soluble in water. There's an OH bond, and it's polar, and that means electrons are pulled towards that oxygen from the carbon. So we get a delta negative. Again, you would have seen this in video 2, where we look at bonding. So alcohols, what they do is they interact via hydrogen bonding. Again, in video 2, if you're not sure what a hydrogen bond is, have a look at video 2. This is because the delta positive charge on the hydrogen is attracted to the lone pair of electrons on the neighbouring molecules. So it's the hydrogen bonding that allows it to dissolve readily in water. So they're very soluble, shorter chain alcohols are more soluble than longer chain alcohols. And this is because with a longer chain, so for example here we've got a short chain because it's only got CH3 on there, but if we have a long hydrocarbon chain attached to that, that bit of the molecule, this bit here, doesn't dissolve well in water because it's a non-polar substance. The only bit that's polar is this OH bit. So if most of your molecule is non-polar, it's going to really struggle to dissolve in water. So alcohols can also hydrogen bond with each other. They don't just have to hydrogen bond with water. Now when they hydrogen bond with each other, that's effectively dictating the melting points and boiling points of these alcohols. So hydrogen bonding, as you remember from video 2, is the strongest type of intermolecular force. So alcohols have higher boiling points than molecules of a similar relative mass. That's from video 1, with no hydrogen bonding, such as, for example, alkanes. And this makes alcohols less volatile, so they don't evaporate as readily as molecules which don't have this hydrogen bond interaction. Okay, so let's look at a summary of the different types of reactions that you will have seen at GCSE and some which you won't have done. So there's loads of different types of reactions in organic chemistry. So we're going to look at each one and look at the examples. There's quite a few here. So the first one is an addition reaction. So addition reactions is where a double bond is broken. We've got two molecules joining together to form a single product. So for example, a classic example is alkenes. Alkenes have that double bond, and so therefore we can open that double bond and add a substance to it. Dehydration reactions is another type of reaction. So this is where a double bond is actually formed as the opposite of an addition reaction. But normally we get water is removed and released from the substance. So for example, ethanol forming ethene to water. So this is the dehydration of an alcohol. Substitution reactions, fairly straightforward. It's just where one is substituted for another. You won't have seen an example like this at GCSE, so I haven't put an example down here, but you will come across substitution reactions quite a lot at A-level. Combustion reactions. So these are, you would have come across these at GCSE. So combustion is where you have a fuel, such as an alkane, and that reacts with oxygen to form carbon dioxide and water if it's complete combustion. Or it'll form carbon monoxide and water if it's an incomplete combustion. So we've got some reactions there of ethane being burnt completely and incompletely. So we've got two different types there. Okay, so another type of reaction is a condensation reaction. So this is just when two molecules join and we get a small molecule is released. Normally it's water or HCl. So as the name suggests, it's condensation. So it's a bit like water being condensed against something. So water's being produced. So that's all that means. Hydrogenation reactions, very similar to addition reactions, except this is a type of addition reaction. Hydrogenation is where you're adding hydrogen to an alkene. So a classic example is the reaction that we've seen before, where you have an alkene, reacting with hydrogen to form an alkane. Cracking reactions, you might have seen these at GCSE. So this is basically where we take a long hydrocarbon chain, normally from petrochemicals, and we break it down into shorter chains, and we use heat. So we use heat such as thermal decomposition, so breaking down a long chain into a shorter one. And the reason why we do this is because sometimes shorter hydrocarbon chains are more valuable. They've got a higher demand for them. So, for example, petrol is a shorter hydrocarbon chain. You might extract crude oil and end up with loads of long hydrocarbon chains which you simply can't sell. Nobody wants it. So thankfully there's a process by which we can break that longer chain into smaller ones, and that's much more valuable to society. So for example, nonane here, which is C9H20, will produce ethene and heptane, which is much better used as a fuel. And displacement reactions, you've seen them already from group 7, so the halogen reactions. So this is basically where this was in video 3, where you've seen halogens. So, but this is where we displace a less reactive element with a more reactive one. So classic example, like I say, is halogen displacement. So sodium bromide and chlorine, for example. Chlorine's more reactive than bromine, which is here, so therefore we get sodium chloride and bromine. So we get a displacement. One swaps the other. Okay, oxidation reactions. So these are normally where an oxygen is gained in a reaction, or a loss of hydrogen. Normally, theoretically though, and this is the official way, and you should know this, you should be able to remember this, you might have seen it at GCSE, is it's actually the loss of electrons. So oxidation is the loss of electrons. And alcohols can be oxidized to carboxylic acids, but you'll see more of that at A level. You might not have seen that at GCSE. The opposite is reduction reactions. So this normally means the loss of oxygen or the gain of a hydrogen, but more precisely, it's actually the gain of electrons. So reduction is the gain of electrons. And carboxylic acids can be reduced back down to alcohols. Again, you'll see a lot more of that in A level. Disproportionation reactions, it's probably the longest word you'll ever hear. Disproportionation reactions you may not have seen at GCSE. Some of you might, depending on the exam board, but this is something you will definitely see at A level. It's basically where an element is oxidized and reduced simultaneously. A classic example is the formation of chlorine-based bleach. So you can make bleach like Domestos, for example, or household bleach is actually sodium hypochlorite, which is NaClO, which is this substance here. Sit there, and basically we make that by reacting chlorine with sodium hydroxide, so chlorine gas with sodium hydroxide, forming your bleach, sodium chloride and water. But basically here the chlorine has been oxidized here, and chlorine is also reduced here, so we've got chlorine appearing in two products. So this is a disproportionation reaction. Electrolysis, you will have seen this at GCSE. So electrolysis is basically where we use electricity to break up a substance that's either molten or dissolved in solution. So a classic example is aluminium. So the extraction of aluminium from its ore and an electrolysis reaction. Elimination reactions. So this is basically where we get a small molecule is removed from a substance and a double bond is formed. So a classic example is eliminating water from an alcohol. This is also known as dehydration in this example. So there is a bit of crossover with some of these, but it's basically where we've got one reactant or one substance and we're removing something from that. So that's elimination. Exothermic reactions. So these reactions is where heat energy is produced. Reactants are higher in energy than the products. And you might have seen this as well at GCSE, but the enthalpy, or delta H as it's known as, you'll see more of this in A level, is negative. For example, a combustion of a fuel. And the opposite is an endothermic reaction. So these are reactions where heat energy is absorbed by the reactants. It's lower in energy than the products, so that the enthalpy change is positive. So this is an example is photosynthesis. That's an endothermic process. Another type of reaction, we're nearly there's a lot of these reactions, as I say, is precipitation reactions. So this is basically where an insoluble solid is produced, like a precipitate. It doesn't dissolve in the liquid that's actually present. And so you will see some you would have seen some precipitation reactions at GCSE as well. Neutralization reactions, you will have seen these again at GCSE. This is where we react an acid and a base together to produce salt and water, and carbon dioxide too, if we have a carbonate that's present. So you can see there's some reaction examples here. So acid plus base forms salt plus water, or acid plus carbonate forms salt plus water plus carbon dioxide. Both are neutralization reactions, so the products are neutral. They don't actually have an acidic or basic nature. Thermal decomposition reactions. So this is basically the breaking down of a substance into smaller substances using heat. So a classic example is the decomposition of carbonates to form calcium oxide and carbon dioxide. And radical reactions, you may not have seen these really at GCSE, but this is just more commonly used in alkanes. Remember, alkanes are unreactive. So radical reactions is where we produce a highly reactive radical. That's just an atom with one electron on its own, like a lone electron, and they're very reactive. And basically, they react with non-radicals to form products, and then products can be another radical. So effectively, it keeps on reacting to form a chain reaction. You might have seen this if you've done it at GCSE. The breaking down of ozone is a classic example when we use CFCs. CFCs are, if they emitted into the atmosphere, they cause a lot of damage to the ozone. So you might have seen radical reactions at GCSE with that if you've done that. Reversible reactions, so these are reactions where there's a forwards and backwards reaction. You may have seen these at GCSE as well, but basically the reactants can be reformed from the products. So there's a forward and a reverse reaction. And finally, redox reactions. So you might have seen these at GCSE as well, possibly. This is basically where you get reduction and oxidation in the same reaction. It's not the same as a disproportionation reaction where you've got one element being simultaneously oxidized and reduced. These are two separate elements. So for example, this one here where we're reacting aluminium with an iron oxide. So aluminium is being oxidized here and iron is being reduced. So we call this a redox reaction. This links in with the other two reactions that we've seen before, which is a reduction reaction and an oxidation reaction. And that's it. So there's a lot of information in there. Organic chemistry is a big part of chemistry. So we've looked at all the equations that's required, that you may have come across in GCSE, and linking it with some of the A-level content and a good library of different reactions as well. So that's quite important as well. There is loads of videos. The full range of A-level videos is available on Allery Chemistry YouTube channel. Please subscribe. And also there is, for this video, there is also a 10-question multiple choice quiz for you to have a go at. It's all electronic, and then it will also mark itself as well. It's got all the answers on there as well. But that's it. Bye bye.